Question number 3 from the 2023 Combined Science Physics Paper 1 Higher Tier is on the topic of electricity. Figure 7 shows how the national grid transfers energy from a power station to some street lamps. Explain how transformer X increases the efficiency of the national grid. Now, in order to increase the efficiency, you don't want to waste energy in the system. How is energy wasted in the national grid? Mainly because as heat energy. Why is that? Because of resistance in the wire. So the idea is to increase efficiency, you want to reduce the heating effect, right? So what is the purpose of transformer X? Now remember, transformer X is a step-up transformer. Transformer Y is a step-down transformer. Right? So step-up transformer, it increases the voltage, right? It increases the PD and reduces the current. Whereas step-down transformer does the opposite. It reduces the potential difference and increases the current. Explain how transformer X increases. Now potential, so for the first mark, you refer to the potential difference. Potential difference is increased, right? So according to the marking scheme, potential difference is increased and the current decreases, right? So that's your first mark, right? Second mark, current decreases. So energy or power loss in the transmission cable decreases, right? As a side note, right, why does it happen, right? Why does it happen, right? Less current means less resistance in the wire, which means less heating, right? If there's less heating, means it's more efficient. The potential difference across the primary coil in transformer Y is 400,000 volts. The potential difference across the secondary coil is 11,000 volts. The current in the primary coil is 660 amps. Calculate the current in the secondary coil or transformer Y. Use the physics equation sheet. So the equation that you're after is V for the voltage or the potential difference in the primary multiplied by the current in the primary coil is equal to the voltage or the potential difference in the secondary multiplied by the current in the secondary. Remember, VI is coming from this equation, V equals IV. So we are trying to conserve the power. So voltage in the primary is 400,000 multiplied by 660 is equal to 11,000 times the current in the secondary. So rearranging the equation, current in the secondary coil is equal to 400,000 multiplied by 660 divided by 11,000. That gives you an answer of 24,000 amps. why is the current in each street lamp less than the current in the secondary coil in transformer Y? Now, looking back, let's annotate this diagram a little bit. So the transmission cables is 400 kilovolts or 400,000 volts. Here, after it goes through this step down transformer, it's 11,000 volts. Now the street lamp operates somewhere between 340 volts, right? And the power station produces voltage around 12,000 volts, right? Now these are rough numbers, but the definite number is the 340 volts. So why is the current in each street lamp less than the current in the secondary coil? Current is used up in the cables between Y and each lamp. Current is not used up. Some of the current is dissipated to the surroundings. The current, heat is dissipated, not the current. The cable between Y and the street lamps have electrical resistance that would reduce the current, but if it's reducing it, that means eventually you won't have enough power later on. The street lamps are connected in parallel. Now that is actually the correct answer. Now the answer for this question 3.3, the marking scheme says the street lamps are connected in parallel. Now I have a feeling if I look at the examiner's report, they would say that most students actually got this wrong, because it doesn't give a lot of information about why the voltage. Ideally, if it was in the class, I would say that usually you would have another step down transformer before it's connected to the street lamps. Right now it clearly shows that they are connected in parallel, right over here. So this is actually a parallel connection. Right. Now let me describe this, explain this. What happens to the voltage when you connect it parallelly? Now remember, if you have light bulbs connected in series to a simple cell, right? If this is 6 volts, the voltage is shared 3 volts and 3 volts. If they are connected parallelly like this, if this is 6 volts, this will be 6 volts and this will be also 6 volts. So according to the question, it should be 11,000 volts. It's a current. Okay. Sorry. Right. So it's not the voltage, it's a current. So what happens to the current then? Right? If I had current of, use a different current, 3 amps. The current is going to be 3 amps across the first bulb and the second bulb. The current doesn't change. Voltage is shared. Current remains the same. Here, if I have a current of 3 amps, it's going to split up into 1.5 amps and 1.5 amps. So as you can imagine, In a street lamp scenario, we have lots of street lamps. They're connected in parallel. So this 11,000 volt, or sorry, the 24,000 amp should be split between all the street lamps, right? Hopefully that makes sense. Figure 8 shows the top of a street lamp. We've got a light sensor and the lamp. The light sensor detects if it is day or night. Figure 9 shows part of the circuit in the light sensor. So you have the power supply, right? The fixed resistor, and what is this? This is a LDR, light dependent resistor. There's a resistor here and the arrows indicates there's light coming through, so it's called a LDR. Explain what happens to the potential difference across resistor R as the light intensity decreases, so when it gets darker. So when it gets darker, when the light intensity decreases, you want the light to switch on, right? So marking scheme answer, right? Resistance of the LDR increases, right? So what happens when the light intensity decreases? Resistance of the LDR increases, so the current decreases, right? Which means the potential difference across R, capital R, decreases. Now again, a little bit of explanation. You need to think about this equation V equals IR, how it actually links over here. So if the resistance, remember the volt potential difference is shared. So if this is 3 volts, this will be 1.5 volt and 1.5 volt. The potential difference is shared. If you increase the resistance, if the resistance is increased, what happens to the current? That should go down, right? Now if the current is actually the same in the circuit, the voltage will increase if you keep the current the same. So if this becomes 2 volts, then this potential difference is going to reduce to 1 volt. So if this becomes 2 volts, this should be 1 volt. So that's what this third bullet point is saying. So the potential difference across R decreases. When the current in resistor R is 20 mA. Now again, in the same paper, here's another conversion for milliamps, right, which is 10 to the power minus 3. The power transferred by resistor R is 60 watts. Calculate the resistance of resistor R. So first of all, let's convert this 20 milliamps to amps, which is 20 times 10 to the power minus 3 for milli, which is 0.020 amps. Now using P equals I squared R, I should be able to find the resistance because I've got the current and the power. So power is 6 equals 0.02 squared multiplied by R. Rearranging the equation, R equals 6 divided by 0.02 squared. That gives me 15 15,000 ohms. So that's 15,000 ohms. That brings us to the end of question 3, and I will see you in question